Hello students, welcome to 8th lecture of chemical bonding and molecular structure. In previous lecture we discussed about the bond parameters. So we saw multiple different type of bond parameters which are required to explain bond. And we discuss about the relationship with these bond parameters with stability of bonds. So now let us move further. So here some important detail about the ionic bond is mentioned, which is also known as Fajan's rule. So some rules are mentioned by Fajan's in term of discussion of ionic bond having covalent character. As mentioned earlier, none of the bonds have 100% ionic or 100% covalent characteristics. More or less, each and every bond contains some of the ionic as well as some of the covalent bond. That means if more than 50% nature is ionic, then we will consider that bond as ionic bond, and if more than 50% character is the covalent character, that means we will consider that bond as covalent bond. So here some rules are mentioned. First, smaller the size of cation and the larger the size of anion, greater the covalent character of ionic bond. So that means size difference will affect the nature. The greater the charge on the cation, the greater the covalent character of ionic bond. For cation of the same size and charge, the one with the electronic configuration n-1 dn ns0, typical of transmission metals, is more polarizing than one with a noble gas configuration ns2 np6, typical of alkali and alkaline earth metal cations. That means we are talking about two different type of metal. One metal belongs to S block, which loses electron and become alkali metal ions. Second type, which fall in d orbitals, that means 3d or 4d or 5d, so on. So some of the metals are transition metals, which belongs to d block elements. Some of the metals are alkali or alkaline earth metals, which belongs to S block. So depending on the type of the metal, it also affects the ionic character. So first and second 2 points are mentioned mainly based on size and charge of cation. As mentioned first point, if size of cation is smaller, and the second point, if charge on cation is more, then covalent character will be more. Why this type of situation occurs? Because smaller size, that means distance of electron from the nucleus will be smaller or less, and less distance represents more attraction, because attractive and repulsive forces both are inversely proportional with distance. If distance increases, then repulsion or attraction both decreases, and if distance decreases, then repulsion or attraction increases. So smaller size of cation actually represents electrons are closer to the nucleus, that's why they will feel comparatively stronger attraction towards the nucleus. If electron feels stronger attraction, that means electrons will be moved slightly towards the cation. Okay, they are more likely closer to the anion, but it will increase the distance. Let us assume like this way. Suppose we have these two situations. These are two ions having exactly same type of negative ion and two different type of positive ion. Charge on both of these positive ion are similar. Let us say both of them carries +1 charge. Okay, and similarly negative ions are exactly same and they are -1 by charge. So smaller size of cation represents electron will feel stronger attraction towards the smaller cation if charges are similar. Why? Because distance of electron will be comparatively less if size of cation is small. So that means if electron pair is comparatively closer in this second scenario, then it will be slightly towards the center in this first scenario. Okay, so this will be the placement of electron pair if we both with each other. That means in second case electron pair is here closer to negative ion, and in first case because of smaller size of cation, cation provides comparatively stronger attraction than the second cation. First cation provides stronger attraction. That's why electron pair will slightly move closer to the center. Okay, and that's why ionic character decreases, covalent character increases. Suppose ionic character of this is, let us say it is 70%. Then in first case it will be less, let us say it is 65%. Okay, so that means second molecule contains 30% covalent character, while first molecule having smaller cation has 35% of covalent character. Now in second case, again we have same type of negative ions, but we have two different type of positive ion. Difference of positive ion is charge. In first ion, let us say we have +1 charge and second carries +2 charge. That means charge on second positive ion is more. So plus charge represents it will provide stronger attraction towards the nucleus. Okay, we are talking about electron. Electron feels stronger attraction towards the higher positive charge, because as we know, like charges repels each other, unlike charges attracts each other. And as the difference increases between two different charges, more and more stronger attraction will be observed. So that means if we consider electrons in first molecule to be here, then in second molecule it will be comparatively closer to the center. Okay, so this is the difference. In first case electron will be here, in second molecule they are present here. So stronger or higher charge on positive ion will move electron towards the center. Okay, so always attraction of negative ion will be strongest if we compare it with the positive ion. So electron won't come closer to positive ion at all. Distance of electron will be always less towards the negative ion, more towards the positive ion. But depending on the charge of positive ion, they will slightly move towards the center. Okay, so that's why higher charge will increase covalent character of ions, ionic molecules. Okay, so higher charge of positive ion, that means more covalent character, and smaller size of positive ion, again more covalent character. Now if you feel confusion regarding to ionic and covalent molecules, then let us quickly talk about it. Suppose we have three different cases. First we have molecule A2. Okay, that means two A atoms are connected with each other. Second we have molecule AB. A atom is connected with B atom. We have AB molecule. And third we have, let us say, AC molecule. A atom connected to C atom. Now in first case, as we can see, we have similar type of atoms. So both of them provides one electron. So electron of first atom will be here and electron of second atom will be here. Okay, we will represent electron of first atom as a dot and electron of second atom as X, so we can distinguish between them, although they are exactly same. So this electron pair will be present exactly at the center, because both of them have similar type of nature. Both of them will equally attract or repel electrons. So electron will stay at the center. Okay, so this has covalent character. We can say that it is highly covalent because electrons are not closer to any of them, and polarity of this molecule will be 0 as well. Now second we have A and B. Now let us say A is more likely to be a positive ion, or it is a metallic by nature, and B is negative ion or non-metallic by nature. So non-metallic elements provide stronger attraction towards the electron, and metallic elements provides weaker attraction towards the electron. So suppose this is the center of the molecule, then electron provided by A will be here and electron of B will be here. They are closer to B and away from A. Okay, so this represents this molecule will be covalent, but it has some dipole moment. Okay, polarity of this molecule is not equal to 0. It has some polarity because B is slightly negative than normal and A is slightly positive than normal. So this is also a covalent bond, but it is polar. First one is non-polar, second one is polar. Now in third situation, let us assume we have A which has highly metallic character. And as we know, normal nature of metal is to form positive ion. They provide very weak attraction towards the outermost electron or valence electron. So nature of A, let us consider it as a highly electropositive. And nature of C, let us consider it as highly electronegative. That means it is like halogen element, which provides strongest attraction towards the electron. Okay, so in this case, because of weak attraction of electron towards A and very strong attraction of electron towards C, electron of A will move in C. That means if we consider it as a bond, just like covalent bond, then this will be the bond, but electrons are extremely close to C, or we can say that electrons are into C. This is the electron of A, which is completely shifted in A, and this is the electron of C itself, which is already inside it. Okay, so this is the center of molecule, and as we can see, electrons are completely shifted inside the C. That's why A behaves as complete positive ion, C behaves as complete negative ion as compared to partial charges on polar molecule. So this is the difference of non-polar, polar and ionic, non-polar and polar covalent bonds and ionic bonds. It depends on, mainly it depends on position of electron. Okay, if position of electron move towards the negative ion, then it decreases the non-polarity, increases polarity, and as the electron pair shift more and more closer to negative ion, it also increases the ionic character. And if electron pair shifts towards the center, it increases covalent character. Okay, so that means covalent and ionic characters actually depends on distance of shared electron pair with atoms present in bond. So same thing is mentioned here. The cation polarizes the anion, pulling the electronic charge towards itself and thereby increasing the electronic charge between the two. This is precisely what happened in covalent bond, that is, buildup of electron charge density between the nuclei. The polarizing power of the cation, the polarability of the anion, and extent of distortion, polarization of anion are the factor which is determined the percent covalent character of ionic bond. Okay, so we discussed same thing here. And now our second theory is valence shell electron pair repulsion theory, or in short VSEPR, Vesper theory. We already discussed about one theory which explains some portion of bonds but not all of them. Okay, we discussed about the limitation and we discussed about the some explanation which can be given by the previous theory. But to overcome the limitation, we have to develop new theory which is already developed. So let us study it. As already explained, Lewis concept is unable to explain the shape of molecule. This theory provides the simple procedure to predict the shape of covalent molecules. Sidgwick and Powell in 1940 proposed a simple theory based on the repulsive interactions of the electron pair in the valence shell of the atom. It was further developed and redefined by Nyholm and Gillespie in 1957. So some of the molecules and their shapes are mentioned in this table. Okay, so let us first observe the table and then we will discuss it further. So first molecule type is AB, that means it contains one positive and one negative atom, or it contains two same type of atom. All of them are linear in shape, as we can see here. Geometry mentioned in last column, all of them are linear. They have different type of polarity depending on their differences of electronegativity. Second, we have AB2 type molecule. We have two different possibilities here. Either molecules will have band structure or linear structure. That means this type of structure, A, B, A or A, B, A. These type of two different possibilities are there. So as we can see in AB2 molecules, some of them have band structure, first to H2 and H2S, and some of them has linear structure, which is CO2. So we cannot predict which of them will be linear or which of them will be bent according to previous theory. Next, AB3 molecule. So as you can see, we have two different type of possibilities again here: trigonal, pyramidal and trigonal planar. That means this type of shape, this is trigonal, pyramidal, more likely tetrahedral shape. Okay, we already discussed about tetrahedral shape. If you are not familiar with tetrahedral shape, then feel free to ask. We will discuss it in three-dimensional shape: tetrahedral, octahedral, trigonal, bipyramidal. All of them we will be discussing them in detail if you find any difficulty to understand this type of shape. Okay, so feel free to ask. And trigonal planar, that means at the center you will have one atom or ion and remaining atoms or ions are present at the exactly corner of perfect triangle like this. Okay, this is planar shape and this is three-dimensional shape. Okay, first one is three-dimensional shape and this is planar shape. And lastly we have AB4 molecule like methane, which is tetrahedral in shape. So these are few examples mentioned here, and we cannot predict the shape of this molecule using previous theory. Okay, so that's why we need to discuss new theory. So let us start with the main postulates of this theory. First, shape of molecule depends upon the number of valence shell electron pairs, bonded or non-bonded, around the central atom. Okay, so in this case we have two different type of electron pairs: bonding electron pairs and non-bonding electron pairs. So what are the bonding electron pairs and non-bonding electron pairs? Let us discuss it first. So let us start with the example of water H2O. We know that oxygen is attached with two hydrogens like this. So as we know, oxygen contains total 6 valence electrons and hydrogen contains one electron according to Lewis structure. Okay, so let us try to draw Lewis structure of this molecule. So oxygen contains 6 electron pair, something like this. Okay, 2 single electrons will be provided to form bond with 2 hydrogens. Let us say electron of hydrogen is X. So this type of situation will arise. Okay, so now as you can see, octet of oxygen is complete. And how many electron pairs we have around the oxygen? As we can see, we have 1, 2, 3 and 4. We have 4 electrons around 4 electron pairs around the oxygen. Now out of these 4, these 2 electron pair is actually shared electron pair between oxygen and hydrogen. That means this is bonding electron pair. Okay, so this will be bonding electron pair. Similarly, this is bonding electron pair as well, but this top electron pair is not shared between oxygen and hydrogen. This electron pair completely belongs to oxygen, so that's why it is called non-bonding electron pair. Similarly, this bottom one is also not shared with any other element, that's why it is also called non-bonding electron pair. Okay, so we have two different type of electron pairs, bonding and non-bonding. Next point is pair of electron in the valence shell repel one another since their electron clouds are negatively charged. Okay, so similar charges or like charges repel each other. So electron pairs will actually repel each other, and that's why they are trying to move away from each other. This pair of electrons tend to occupy such position in space that minimizes the repulsion and thus maximizes the distance between them. So as far the electron pair is from each other, more or less will be the repulsion. As mentioned earlier, if distance increases, then repulsive or attractive forces decreases. Repulsive and attractive forces are inversely proportional with distance. Simple example, use two different magnets, magnet A and magnet B, and suppose opposite poles are pointed towards each other. Okay, so when we place them closer to each other, they will feel stronger attraction to each other and they will attract each other. But if we are placing two different magnets 10 foot apart, that means no attraction will be provided from each other because distance is too large. Okay, so similarly, if we put two similar poles of magnets closer to each other, then they will repel each other. If your distance between them is 1 centimeter, then repulsion will be strong. And if distance between them is 100 meters, then repulsion will be extremely low, or there will be no repulsion at all. So distance is inversely proportional with attraction or repulsion. Next, valence shell is taken as a sphere with the electron pair localizing on the spherical surface at minimum distance from one another. Multiple bond is treated as if it is a single electron pair, and then 2 or 3 electron pairs of multiple bonds are treated as a single super pair. That means if we have double bond or triple bond, we will consider it as one single bond or one single cluster of electron. That means we do not consider double or triple bond as separate electron pairs. According to this theory, we will consider them as a single unit. Where two or more resonance structures can represent a molecule, the Vesper model is applicable to any such structure. That means we can apply this model to all of the resonating structures separately. Okay, that means this is useful for resonating structures as well. Now, repulsive interaction of electron pair decreases in the order as mentioned below. Lone pair, that means non-bonding electron pairs repels each other strongly. As mentioned earlier, we have two different types of electron pairs, bonding electron pairs and non-bonding electron pairs. And non-bonding electron pairs are also referred as lone pairs. Okay, so lone pair represents non-bonding electron pair. So these two type of electron pairs gives these type of order of the repulsion. Strongest repulsion will be felt between two lone pairs. Then second strongest repulsion will be between one lone pair and one bond pair. And weakest repulsion will occur between two bond pairs. Why? Because lone pairs are localized and bond pairs are delocalized. What it means? Suppose let us use example of oxygen again. So when oxygen is attached with two hydrogens, it has two bonding pairs like this and two lone pairs like this. So as mentioned earlier, positive ions also attracts electron pair. Okay, attraction of positive ion will be comparatively less than negative ion, but still they provide some attraction to electron pairs. So that means these bonding electron pairs also feels some attraction towards the positive ion, but this non-bonding or lone pairs only feels attraction towards the oxygen, whereas these bonding pairs feels attraction towards the oxygen as well as towards the hydrogen. That means hydrogen will pull this electron pair slightly away from the oxygen, and these two electron pairs, lone pairs, do not feel any kind of attraction out of oxygen. So they are comparatively closer to oxygen, and these bonding electron pairs are slightly away. If we compare it with these lone pairs, then distance of bond pairs will be comparatively more. And what happened with increasing distance? So understand it like this way. Suppose we have a molecule having two electron pairs. Okay, and let us say distance between two electron pair must be 10 angstrom to minimize the repulsion or to increase the stability. Okay, this is our minimum least requirement. So suppose we have a smaller ion. This is the center, and this distance represents 10 angstrom. Okay, so that means if two other ions are attached or two other atoms are attached, then they must be present here. Okay, to fulfill the requirement of distance. These electron pairs has 10 angstrom distance from each other. So this will be our angle. Now assume a second atom comparatively larger in size. So 10 angstrom distance will be here. So electron pair will be placed here if they are away from the center, and as we can see, angle is reduced. Although distance of electron pair is still the same, but angle is reduced. If distance of electron pair is comparatively less, then angle will be increased, and if distance of electron pair is more from the nucleus, then it can be reduced, angle can be reduced. Okay, so this is the reason if electron pair feels repulsion from outside, then they will move away from the nucleus, as we can see in case of oxygen and hydrogen. These two electron pairs are bonding electron pairs. That means they feel attraction from hydrogen. That's why they are away from the nucleus or oxygen. And two non-bonding or lone pair are present above or below in this case. So these non-bonding electron pair do not feel attraction from outside. So that's why they are closer to nucleus or atom. That's why they have to move away from each other, and angle will increase to maintain same distance. So simple thing, lone pairs are closer to the nucleus, that's why they need broader angle, and that's why they repel strongly. And bond pairs are away from the nucleus, that's why they feel less repulsion. Nyholm and Gillespie redefined the Vesper model by explaining the important difference between the lone pair and bonding pairs of electron. While the lone pairs are localized on the central atom, each bonded pair is shared between two atoms. As a result, lone pair electron in a molecule occupy more space as compared to the bonding pair of electron. This results in character repulsion between lone pairs of electrons as compared to the lone pair bond pair and bond pair repulsion. This repulsion effect results in the deviation from the idealized shape and alteration in bond angles in molecule. Okay, so what we are talking, we will discuss it in detail in upcoming points. For the prediction of geometrical shapes of the molecule with the help of Vesper theory, it is convenient to divide molecules into two categories. First is molecule in which central atom has no lone pairs, and second, molecule in which central atoms has one or more lone pairs. That means in first category all of the electron pairs are bonding electron pair. In second category we have some lone pairs. Table 4.6 shows that the arrangement of electron pair about a central atom A without any lone pairs and geometry of the molecules or ions of the type AB. Table 4.7 shows the shapes of some simple molecules and ions in which the central atom has one or more lone pairs. So table 4.8 explains the reason for the distortion in the geometry of molecule. Okay, so first of all let us observe the tables 4.6, 4.7 and 4.8. This is table 4.6 and all of this molecule contains only bond pairs, no lone pair. So first we have two electron pairs and the shape of molecule is linear. Example BeCl2 or HgCl2. Then we have three electron pairs. So maximum distance will be observed if angle is 120. In first case, maximum distance if two electron pairs are there, then maximum distance will be observed when we have 180 degree angle. For 3 we have 120 degree angle and shape will be triangular planar, as for example BF6. If you have 4 electron pair, then shape will be tetrahedral. That means angle will be 109.5. It is 3-dimensional shape. First shape, that means linear shape, is only 1-dimensional. Second shape, triangular planar, is 2-dimensional shape, and from the 4 electron pairs 3-dimensional dimensional shape will start, which is tetrahedral in this case. Example CH4 and NH4 plus. Then we have 5 electron pairs, which gives us trigonal bipyramidal. It is again tetrahedral shape. And if you have 6 electron pair, then you will get octahedral shape. It has total 6 electron pair. Now naming of tetrahedral and octahedral. Tetra, that means 4, and octa, that means 8. Now hedral, that means plane. Okay, so tetrahedral shape contains 4 planes and octahedral shape contains 8 planes. If we count the electron pair in tetrahedral, then it will be 4, and if you count it in octahedral, then it will be 6. Okay, so electron pair or corners are not reasons for the naming of this shape, but planes are there. Okay, so number of planes represents the naming scheme of these shapes. 8 planes, that means octahedral, and 4 planes, that means tetrahedral. And when we place two different tetrahedral shapes on top of each other, it will be something like trigonal bipyramidal shape. Okay, so if we count the total number of planes in trigonal bipyramidal, then it will be 6. Okay, so examples are mentioned here. All of this example contains only bond pair. Now next table has bond pair as well as lone pairs in this shape. So first type is molecule of A, B to E. Now actually it contains only 3 elements, one A and 2 B, but E represents lone pair of electron. Okay, so number of E actually represents number of lone pairs and number of B represents number of bond pairs. So that's why it is mentioned in the second column number of bonding pairs is equal to 2 because B is equal to 2, and number of lone pair is 1 because E is equal to 1. So possible arrangement of this molecule will be something like this. All of these 3 electron pairs will try to move away from each other, and that's why they will form this type of triangular shape. So arrangement of electron pairs is trigonal planar, but shape of molecule is mentioned band. Reason for that is in this location we do not have any element. This electron pair actually belongs to A, so nothing is present on the top of the A. So shape is actually band shape. That means lone pair of electron do not contribute in shape, although it affects the shape, but no contribution from that side. Okay, because of that lone pair, molecule will be look like band structure, but it won't provide any physical form inside the shape. So let us understand these two structure, that means trigonal planar shape mentioned here and triangular planar shape mentioned in previous table. That means all of the 3 pairs are bond pairs, then what will happen, and if one of them is lone pair, then what will happen. So this is our molecule. At the center we have A and at the surrounding we have B. That means gray ball represents atom of A and blue balls represents atom of B. So this is triangular shape, and if we observe it from different angles, then you will notice it is planar shape. Okay, as you can see, it is 2-dimensional shape. Okay, so as we can see, it is 2-dimensional, and if we connect these surface points in this area or in this structure, then you will notice shape of this atom or molecule. So if we connect these surface points in this shape, then as we can see, we have a triangular planar structure. Okay, so this is a triangle and it is planar. Okay, as we can see from all the direction. So this is AB3 type molecule, and all of the 3 electron pairs are bonding electron pairs. Now what happened if we remove one of the replace one of the bonding electron pair with non-bonding electron pair? So now this will be our shape. Now we replaced this element with a lone pair of electrons. So now this element is no longer present here, and we have lone pair on the top of this central element. So all the functioning or all the effect of this lone pair on the shape of molecule is it will repel bond pair present here. Okay, we have a bond pair present here which feels repulsion from this lone pair. Okay, so this electron pair will only provide repulsion but no physical part of molecule. That's why now our molecule is bent. Okay, so this will be the effect of one lone pair in total 3. Now second is AB3E type. That means total we have 4 electron pairs, 3 are bonding electron pair, 1 is non-bonding electron pair. So if we have 4 electron pair, then as mentioned in previous table, with the help of 4 electron pair we can create tetrahedral shape. But if all of them are bonding, then it will be tetrahedral molecule. But as we can see here, we have 3 bond pair, 1 lone pair. That's why shape mentioned is trigonal pyramidal. So first of all, this is a AB4 type molecule. At the center we have one A and 4 different B, which represented by blue spheres or balls. So in this shape, as we can see, we have a tetrahedral shape. That means 3 bottom points are present at the corner of the triangle and 1 at the top. But this shape can create tetrahedral all the side or triangles all the side. So now first of all, to represent tetrahedral shape, let us connect all the blue spheres with each other. Now as you can see, we connected all the blue spheres with each other, and this is tetrahedral shape. Now if we reduce the transparency of the surface, then we can see proper tetrahedral shape. Okay, so this is tetrahedral shape. That means 1 2 3 and 1 at the bottom. We have 4 triangular planes attached with each other. If we observe it from the top, then it will appear like this. Mostly tetrahedral shape will be represented like this. So this is a tetrahedral shape, and without any surface point connected, it will look like this. At the center we have one atom and surrounded by 4 other type of atom. This is AB3 type structure. So all of the 4 electron pairs are bonding electron pair. But what happened if we remove one of the bonding electron pair and we place non-bonding or lone pair instead? So if we remove top sphere and replace it with electron pair, then shape will be something like this. This shape, bottom shape, now top sphere is not a member of our structure. Okay, so this is the shape we need to concentrate on. So this is triangular pyramidal shape. Shape of ammonia molecule is something like this. Okay, if we connect all the points, then it will appear like this. Okay, so this is triangular pyramidal shape. That means a pyramid which has triangle base. Okay, so this is triangular pyramidal molecule having 4 electron pairs, central atom having 4 electron pairs, but out of 4, one is non-bonding electron pair which is present at the top. That means electron pair is present here, and because of the repulsion of this electron pair, these 3 bonding electron pair tend to bend. Okay, and that's why this type of bent structure appears. Okay, so with the 4AB3E type structure, you will get trigonal pyramidal structure which we observed. And next is same type. Again we have 4 electron pair, but out of 4 we have 2 bondings and 2 non-bonding electron pair. So let us again repeat our structure. So as we discussed in this structure, we have 4 electron pairs, and out of 4, 1 is non-bonding electron pair and 3 are bonding electron pair. But now we have to remove one more bonding electron pair, and we will place one non-bonding electron pair, and we do it with this atom. Okay, we will replace this atom from the here, and we will place one non-bonding electron pair instead of it. So if we do so, this will be our shape. So as we can see, we replaced 2 electron pairs, and now we have 2 non-bonding electron pairs and 2 bonding electron pair, and shape of our molecule now it will be angular. Okay, so we just removed some elements from that locations, but their effects will remain. Okay, we replaced elements with non-bonding electron pairs, so repulsion will be present there, but shape from that side will be removed. So that's why with one bonding electron pair, one non-bonding electron pair and 3 bonding electron pair, it will be pyramidal shape. With 2 non-bonding, 2 bonding, it will be angular, as we can see here. Now next is a total 5 electron pair, AB4E, 4 bonding and 1 lone pair. So arrangement of electron pairs will be triangular bipyramidal, just like mentioned here. So first of all, let us see what is triangular bipyramidal shape. So this is our triangular bipyramidal shape. At the center we have an atom surrounded by 5 other atoms. So from this angle, as we can see, 3 of the atoms are present at the corner of perfect triangle, okay, and 2 atoms are present at top and bottom, which is perpendicular with the plane of triangle. So let us create triangle at the center first. So as we can see, we have perfect triangle and 3 of the spheres are present at the corner of perfect triangle, and 2 spheres are present at the top and the bottom of triangle. If you compare the length of these bonds, then you will notice 2 bonds which are present at top and bottom of the triangle or perpendicular with the triangle are longer than the bond of triangle, okay, which is apparently observable from the structure. And if we provide the length measurements, then you will notice distance between the triangle corner sphere and perpendicular sphere is 1.15 and 1.63 from this structure, okay. So same thing is applicable with each and every molecule. In triangular pyramidal shapes, you have 2 different type of bond lengths, axial and equatorial. Shorter bond lengths are equatorial bond lengths and longer are axial bond lengths. So now let us complete the structure and observe triangular pyramidal shape. So if we connect all the centers point, then you will notice we have 2 different triangular pyramidal shape. One triangular pyramidal shape at the top, as you can see here, just like tetrahedral shape, and one at the bottom, just like tetrahedral shape, okay. So we have 2 triangular pyramidal attached with each other, and you will get triangular bipyramidal shape, okay. So this is our triangular bipyramidal shape without any lone pair of electron. Now let us observe one lone pair is placed instead of bond pair, then what happened. So as we discussed, we have 2 different type of bonds, one axial and one equatorial. In this structure you can see that one equatorial bond is removed. That means triangle is corner of the triangle is removed. That means in our shape we will remove this point, and let's see what happened. So we removed one corner of the triangle, and the remaining shape, as we can see, this type of shape will be observed. That means we have one angle like this which behaves as a support of a seesaw, okay. So this is our seesaw like shape. That means we have this type of angular shape from these 2 points and a straight shape from these 2 points. So seesaw like structure will be observed. Similarly, in next point we have same trigonal bipyramidal shape, but instead of one we will place 2 lone pair of electrons. So trigonal bipyramidal shape with 2 lone pairs, that means we will remove 2 corner of triangle and you will get T shape. Let us observe it. Okay, so in this shape let us remove 2 of the points of the triangle. Okay, so first of all let us remove the green lines which represents the outer surface but not actual bonds, and now let us remove these top 2 points of the triangle. Okay, so as you can see we removed 2 elements from the top and bottom, and now you will get a T-shaped molecule. Okay, so trigonal bipyramidal shape with 2 lone pair of electron, that means still these pairs are repelling the shapes but they are not part of the shape. That means 2 electron pairs will be present here but they are not longer the part of the shape, and that's why you will get T-shaped molecule. Next is a octahedral. So let us observe normal octahedral shape and then we will replace it with electron pairs. So this is our octahedral shape. We have 6 atoms surrounding. So in this shape, as we can see, we have total 6 corners. But to observe proper octahedral shape, we have to connect all of these surface points with each other. Okay, so now we connected all the surface points with each other. So notice that if we divide this shape in half, that means like this, okay, only half shape is visible on screen. So you will notice this shape is like pyramid, Egypt's pyramid. Okay, so top side you will notice we have 4 segments or sections, triangular sections and a square base. Similarly we have second pyramid at the bottom. So you will notice we have 4 planes at the bottom and 4 planes at the top. That's why we have total 8 planes, and this shape is called octahedral. Okay, so this is our octahedral shape, and all the blue lines, actually we represented it to represent the shape. They are not actually bonds. Okay, black lines represents bonds, not the blue, light blue lines. Now if we replace one of the electron pair with a non-bonding or lone pair, then what will happen? You will get square pyramidal shape, as you can see here. In A, B5, E type, you will have 5 bond pairs and 1 lone pair. So in our 3D shape, let us remove this point. That means we have to remove this bond from this side, and we have to remove all of the lines connected with this point as well. So this will be our structure. We have to ignore the bottom sphere. Now it is not part of our molecule. We replaced that sphere or atom with lone pair. So as you can see, we have a pyramidal shape remaining. Okay, so this is pyramidal shape with 4 bonding electron pairs, which represents these black lines, and 1 non-bonding electron pair which will be present on the center sphere. That means this sphere. And last structure is AB4E2. That means we have to place 2 lone pairs, and that means we have to remove 1 more electron pair or element from our structure. Now from this structure we will again remove one of the point present here. Okay, so let us remove this atom and let's see how shape changes. Now to remove that sphere, we have to remove this bond and all the line connected to that point. That means we have to 4 green lines, blue lines and 1 bond. Okay, so this will be our shape. We removed one sphere which was the part of the structure initially, and now we have this type of planar structure. Okay, so as you can see, top and bottom sphere, now they are replaced with non-bonding electron pair or lone pair. And now what is our shape? As you can see, we have planar shape. This is 2-dimensional square shape. So with 4 electron pair, bonding electron pair and 2 lone pair, you will get this type of planar shape. Okay, 2-dimensional square planar shape. Okay, so we discussed about these 2 tables. First table which represents all of the bonding pairs, second table bond pair plus lone pairs, and third table is actually the discussion of the 3-dimensional structure which we already did. So read it yourself, table number 4.8. If you find any difficulties, then feel free to ask. We already discussed these things in 3 dimension with the 3-dimension shape. So still if you find any difficulty, then you can ask me, and then we will start with our next point, 4.5 valence bond theory, in next lecture.